Okay, so the big problem when we build our bridge is that we are going to have to end up putting a load on it. And we want our bridges to hold the biggest load. So how do we build a bridge that can hold a big load without breaking? That's going to be the topic of this little video lecture. We're going to learn a little bit about the forces that are put on a bridge or on a structure and how we might dissipate those. So go ahead and set up your notes. You can call this forces on structures notes, and go ahead and draw your 2 columns with your big ideas and supporting details. If you need to, pause the video really quick and we'll get started. Okay, forces on structures. So all structures are built to withstand a variety of external and internal forces. And when they're built, they're designed to either transfer those to somewhere else or to dissipate them or spread them out. So some of the vocabulary that we're going to be looking at, so you should put this in your big ideas, is the first one is dead load. Dead load. Dead load is the force of the structure itself. So a bridge needs to be able to hold itself up. A skyscraper needs to be able to hold itself up before anything else is added to it. So dead load is just holding up itself. Whereas live load is the outside forces. So what else is going to be put onto this bridge or building? What else is it going to be exposed to? So for example, we might have wind or traffic or snow, but whatever other structures, it could just be pedestrian traffic. All of those need to be taken into consideration. Okay, so the first type of force, and we're going to cover 2 basic types of forces here, because these are the ones that are most commonly experienced by your bridge. So first is tension. Tension is any kind of stretching or pulling force. So anytime something is pulled, so for example here we've got backpacks, backpack straps. Obviously the more weight you have in your backpack, the more tension the straps are experiencing. Here we just have someone pulling a wagon here, and of course the rope is under tension, this part is under tension, the part where the little latch is attached is under tension, and his arms are actually under tension. So the problem is when tension forces are exceeded, snapping can occur. And that can occur, of course, in your backpack strap. It can occur if you're stretching a rubber band. If I were to take my ruler here, this one is a kind of a flexi ruler, but when I bend it, I'm putting the top part of this ruler under tension. If I continued and continued and continued to do it, it could snap. So we don't want that to occur. We want to try to reduce the chances that the bridge is going to snap under tension. So let's look at what this looks like in a bridge. So some common examples of bridge experiencing tension forces. So the first here is a beam bridge. I'll get my pen over here. When a load is put on the beam bridge, so if it's put here, it pushes down on the beam of the bridge. Now that causes it to stretch kind of like my ruler, right? So in this case, the bottom part of the bridge is under tension. This bottom part of the beam is being pulled apart and stretched. And we know that beam bridges struggle with too much load. So if you get too much tension under that, you're going to cause some snapping of the bridge. Now a suspension bridge takes advantage of tension and transfers that throughout the bridge. So we know that in a suspension bridge, the roadbed is being supported by the cables. Now the cables are pulling, stretching, holding up that roadbed. And that seems like it would be kind of counterintuitive that you would not want all that load put on those cables. But what a suspension bridge does is then transfers that to the giant towers, which are then put under compression, which we'll talk about in a second, and to the anchorages, the part where the bridge is actually anchored to the ground on the other side. And it's able to transfer that load out, spread it out, dissipate it, so that it doesn't buckle or snap. Let's get this. Okay, so the next type of force here is a compression force. A compression is just exactly like it sounds. It's a pushing or a squeezing force. So anytime you push or squeeze on something, the material is under compression. Really common example, of course, is if you're sitting on a chair, the legs of the chair are under compression. If you're pushing on anything, the material is under compression. So, unfortunately, if compressive forces are exceeded, buckling can occur. And this is an example of a steel beam here that buckled because of excessive compression forces. And we do not want that to happen in our bridges. Now, some bridge designs work really well with compression forces, and some materials work really well with compression forces. The bricks or the pieces of a, what is this called? An arch bridge are under compression. So when the load is put here, it pushes down on the bridge, and then it pushes on each individual part of the bridge until it gets to whatever it's anchored to, like in the Hoover Dam Bridge, the canyon walls, which then can absorb an enormous amount of weight. Again, I mentioned with tension forces, when the tension in the cables is applied to the towers, it puts the towers in compression. So you have these gigantic steel or even stone towers that are pressing down into the earth, which can absorb an enormous amount of stress. Oops. Okay, so when you're building your bridge, you want to keep in mind the different forces that are going to be put on it. We're going to do that in the next activity.